Hello everyone, my name is Rozemarijn Roes. I'm a bachelor student from Utrecht University, and today I will talk to you about our paper, an Emotional Respiration Speech Dataset. It is written in collaboration with PhD student Francisca Pessanha and Dr. Almila Akdag, who are also from Utrecht University. With our paper, we present an emotional respiration speech dataset. The objective of the researcher reported in the paper is to record breathing patterns during speech and non-speech segments under induced emotional responses. With our experiments, we produced 400 minutes of emotional respiration during and not during speech. The emotions that were induced were annoyance, happiness, sadness, and calmness. On the right, you can see an example of 2 respiration patterns during happy emotion. Later on in this presentation, we will tell you all about how we collected this data. But before we do that, we will talk a bit about why this paper is relevant in general, and more specifically, why to this workshop. To understand this, we need to go back to basics. It is important to know that humans infer information from certain somatic signals. Think about what you can infer from this picture. Purely looking at the body posture, you could maybe think this person is angry or annoyed. Or, if one hears someone speaking soft and stuttery, they could be observed as shy or afraid. And lastly, if someone is breathing very fast, they could be anxious or angry. However, that is how nonverbal communication works between humans. To be able to recreate this natural interaction with human-like embodied agents, we need to be able to generate realistic nonverbal behaviors. An agent just stating it's sad, without any other cues, will not create a realistic effect on the receiving end. So we need a dataset of nonverbal behavior to be able to create more realistic agents, but also because we need to be able to use somatic signals as input for more realistic feedback in agents. One important factor to understanding and modeling realistic behavior is emotion. Emotions serve as a signal of not only the mental state, but also the possible needs of the other person, and they can even affect the emotions of the one that is observing them in the other. By adding non-verbal cues, one is better at understanding the other's emotion. When looking at VR, we see that adding respiratory cues to virtual agents help humans detect the displayed emotions more accurately. A study also showed that adding breathing motions to something as unhuman-like as a robotic arm that is carrying out manipulation tasks alongside human coworkers improves its appeal and lifelikeness of the robots to its coworkers. These examples of the literature show that respiration can be important in modeling emotions and other realistic behavior. By researching the literature more thoroughly, it became clear that a lot of studies show the relevance of breathing in this process. For example, Domelo et al. Also emphasized the importance in respiration with signaling the intensity of emotions. However, the existing literature has some limitations. There seem to be scarcely any databases for affect analysis with breathing ground truth to learn how affect and breathing correlate. Emotional speech databases typically contain utterances colored by emotional intonation instead of natural conversation and lack breathing annotations. For example, with Paula, the breathing does not take place during speech, plus they used fixed breathing. It misses emotional and contextual respiration. So the question is, how could we get better databases? For this, we needed to explore what is already known about realistic breathing. Thus, we looked into existing literature that reported which emotions trigger which kind of respiration. There's quite a variability in the results of the different studies. However, we can still take some general conclusions. A rise in arousal during negative emotions, such as anger, fear, and anxiety, creates more shallow and rapid breathing. Similarly, positive emotions with high arousal increase the respiration rate, whereas low arousal decreases it. In short, the levels of arousal, as well as valence, seem to trigger similar variations in breathing rhythm, and similar influences of different emotions on breathing can be explained via commonalities between them. Due to the still inconclusive results and the fact that most previous research focused generally on visual emotion induction, we wanted to think of an experiment design where the stimuli were more personal and thus hopefully more strong in their emotion induction. For this, we used music. We let participants choose the songs they would have to listen to for each of the 4 emotion categories. We chose 4 emotions as they seem to all cover one of the 4 possible valence arousal combinations: annoying, happy, sad, and calm. On the right, you can see an example of 4 songs that different participants chose for the different emotions. Participants were recruited through social media via convenience sampling. In total, 20 people took part in the experiment. They mostly consisted of university students, and their age ranged from 18 to 29. 2 to 3 weeks before the experiment, each participant filled in a digital survey to submit songs that made them either happy, sad, or calm and annoyed. Participants were randomly and evenly divided into one of either emotion pairs through a randomizing option in the survey. For each emotion category, we collected at least 3 songs, where each song was weighted on a 1 to 5 Likert scale on how intensively a song triggers the emotion. For example, 1 would indicate that someone would be a little bit happy, and 5 if the song would make them extremely happy. For each participant, we selected 2 songs with the highest intensity scores from each category. We prepared 90-second fragments for all the selected songs to be used during the experiment. The affective states of the participants were measured through a digital version of the self-assessment mannequin on a 9-point pictorial scale for valence and arousal values. Respiration was measured with the biosignals plug's piezoelectric respiration sensor, or also a respiration belt, and a Bluetooth-controlled microphone attached to the neck. 1 sensor was placed around the thorax and 1 around the abdomen. The experiment consisted of 1 session for each participant and lasted approximately 30 minutes. Participants were first given a short explanation of the experiment. Then the belts and the microphone were attached, and a test round was recorded. At this point, the experimenter left the room to avoid observer effects. The baseline condition after calibration lasted 45 seconds. After that, 4 musical fragments were played in a semi-random order for each participant to cancel out odor or fatigue effects. All the songs of one emotion condition were always played one after the other. After each song fragment, participants first filled in the SAM questionnaire and then talked about their experience of listening to the song for a maximum of 45 seconds. That was followed with an interstimulus period of 30 seconds to reduce possible emotional effects induced by the fragments that were played before. An experiment interfaced on a monitor guided the participants through every step. Regarding the results, we were considering 2 questions. The first one was whether the music truly did induce certain emotions. The second one was the question of how these emotional stimuli affected respiration. To evaluate whether the songs elicited expected emotions, we analyzed the self-reported valence and arousal levels. The results showed that songs for almost each emotion type influenced the valence levels of emotion strongly, in the expected manner, as shown in the table on the left. Only happy music did not have significant effects. However, there were no significant strong effects on the experienced arousal levels. When looking at non-significant effects, the happy music did seem to increase arousal, as did annoying music. You can also see this in the model to the right. Sad music did not have any clear influence on arousal. Lastly, calm music seemed to decrease arousal, but only after the second song. These results indicate that it may take more time to influence arousal with music. The lack of significant effects may also be due to the small sample size. We will now demonstrate the measured respiration patterns by taking a participant's respiration as an example. The figure displays 45 seconds fragments of the chest and abdomen respiration patterns during the baseline, so during no music listening, as well as during listening to songs and the speech episodes that come after listening. When we compare chest and abdominal respiration, we observe that the chest respiration is more sensitive to the effects of different emotional songs compared to the abdominal respiration. You can see that the abdominal signal has a similar number of respiration cycles and amplitude for each song. Furthermore, the music condition induces a different type of breathing compared to the no music condition. This was visible across all experiments. A last observation can be made when looking at the speech graphs. You can see the respiration become deeper and sharper during speaking than during listening. And this is more dominant in the abdomen than in the chest respiration. of this, we cannot conclude a lot with certainty, as these are merely observations. The most important possible conclusions for virtual agents is, however, that the chest respiration should take precedence in emotional respiration synthesis for virtual agents over abdominal respiration when creating respiration patterns during the display of emotions. For speech, this is the other way around. The abdomen is more important. To evaluate the effects of music on respiration, we analyzed the respiration data of all participants. Multiple statistical analyses were conducted, but due to space constraints, we only discussed the averaged respiration feature values for each emotion category in the paper. Similar to our evaluation of valence and arousal levels, we compare respiration features of each emotion category to the baseline condition. We observed that among all the respiration features, there was only one statistically significant difference between at least two of the mean chest respiration peak-to-peak distances during the happy-sad condition. Note that the peak-to-peak distance is the distance in seconds between two respiration cycles. A post-hoc pairwise comparison then showed that there was a significantly lower peak-to-peak chest respiration for sad music compared to no music. This suggests that breathing cycles become shorter when listening to sad music compared to no music listening. There was no significant difference between no music and happy music, nor between sad and happy music. Even though there was only one significant effect, when analyzing the mean differences of respiration features, certain tendencies still became visible. For example, sad music deepens the abdominal respiration, while both the chest and abdominal respiration are faster than when no music is played. Happy music has a similar increasing effect on respiration frequency, but may induce a more shallow chest respiration pattern. Calm music shows a non-significant tendency to lower the abdominal respiration frequency. And annoying music shows an opposite pattern, where the abdominal respiration frequency is higher. The results show that there are effects of musical emotion elicitation on respiration. These results can be used to create more realistic emotional breathing behavior in agents. However, the experiment also created the dataset I was talking about earlier. This dataset can provide realistic respiration as input for more realistic feedback in agents. And just to repeat, the dataset does consist of audio recordings of 20 participants while they listen to self-selected songs that trigger emotions from the two emotion pairs, happy-sad or calm-annoying. You can see here to the left that it consists of self-reports, video data, audio data, and respiration belt data. The video data could be used to analyze emotional expression even further. Even though the relation between music and emotion elicitation has been established strongly in the literature, this dataset is the first to use music for emotional speech. However, as we base our analysis on self-reports at the end of each listening episode, we do not have a more nuanced labeling throughout the listening and speech episodes. We also need to further test if the music-induced emotion is similar to emotions experienced and expressed during conversations. We need to note that there is a potential bias that comes with self-annotations. And lastly, even though we provide a vast dataset, we still need to consider the small sample size when looking at the effects of musical emotional elicitation on respiration. The effects on arousal may be much stronger when the study is repeated with a larger sample size. Despite these shortcomings, the analysis of the dataset still brought interesting insights and future directions. To convey sadness or happiness, an agent should be programmed to have a higher respiration rate. Obviously, breathing patterns are just one aspect of creating the appearance of emotions, but they are strong, and even a non-anthropomorphic design, such as a single robotic arm, becomes much more lifelike via the addition of breathing motions. And these are the references we used for this presentation. So before we end this presentation, I wanted to share our contact details if you still have questions after the Q&A, or if you just want to see the paper, you can email one of these 3 emails. And lastly, I want to thank you for listening.